Hello, everybody. Welcome to this month's Future in Space Hangout. My name is Tony Darnell, and I am your moderator from the deepastronomy.com website as well as the Deep Astronomy YouTube channel. And I think we've got another really great hangout planned for you this evening. We're going to be taking a look into the future of X-ray astronomy, and we're going to be talking with some experts in the field who are looking now towards our future, and we're going to learn not only what X-ray astronomy is like right now, but what are some of the things that it teaches us about the universe in this very interesting wavelength. And in particular, we're going to be discussing the X-Ray Surveyor mission, which is in the planning stages now, and we're going to be going over some of those things as well. It's part of the I think it's being discussed in advance of the 2020 decadal survey, so we'll find out all kinds of cool things about that. This hangout, if you don't know what it's for or what we're doing here, every single month on the third Friday of every month, we talk about space, and we talk about the future of space and what's going to happen in space, not only with humans going to different spots in orbit and then maybe up into interplanetary space, but also the science, the future of the science that we're going to be doing, future space probes. And we look at all of these different aspects, from the technologies that go into the future to some of the programs that are being discussed. So I like this because it involves a lot of the experts and members of two really great organizations that happen to be very similarly named: the American Astronomical Society and the American Astronautical Society. Members are highlighted with their science from these groups, and both of these organizations help with getting the word out about what their members are doing. So I want to give my appreciation to both of those great organizations, and we also want you to be. This is a Google Hangout on air, so that means you can interact with us. Leave our guests questions and comments, and there's two big ways you can do it. You can do it with the chat window. If you're on YouTube, just go on YouTube and leave a comment on the chat window. I'm looking at that right now, and I can see them as they come up. And if it's relevant to what we're talking about at the time, I'll interject it right then. Otherwise, I'll read them at the end of the hangout. And the second way that you can interact with us, tweet at us, as it were, is on Twitter using the hashtag #FutureInSpace, which I have on my lower third down here. So I'm also looking at that hashtag as well. So we hope you'll have some questions and comments for our guests. I already see Andrew Planet has one for us, which I'll be getting to momentarily. So here we go. I'm going to introduce my co-hosts for this Hangout series. First up is Dr. Harley Thronson, coming off a really big week for the Humans to Mars Summit. He is a astronomer at NASA's Goddard Space Flight Center. Hi, Harley. How you doing?
Doing well, doing outstandingly. We had a great summit on developing concepts and developing the science community for affordable human missions to Mars this past week.
I know what was great about that is you guys actually live streamed most of it, and I was able to see it and as if I was there. So that was really a cool thing.
Yeah, if the folks out there want to take a look at it, look at the Explore Mars Incorporated website, and they will stream almost, it'll be archived almost the entire set of presentations.
That's right, because there was Buzz Aldrin was talking, Bill Nye had talked and did some stuff, John Grunsfeld did some things, Robert Zuber,
the author of The Martian,
wrote The Martian, also was there talking about different aspects of going to Mars. So that was a really great conference. And also joining me, and he just muted himself, so unmute yourself, Alberto, Dr. Alberto Conti from the Northrop Grumman company. He is the innovation scientist and basically all-around amazing person. It's good to see you again, Alberto.
Amazing person. Stop drinking.
Stop what? Stop drinking? Oh.
Stop drinking. Yeah. Thanks. It's good to see you, Tony. Hi, Harley.
Good afternoon, Alberto.
All right, so just as a quick warning, Alberto's on internet Wi-Fi again, so he might be in and out as we go. So, all right, let me set up the hangout today. I'm going to read this from. I did a search on the X-Ray Surveyor mission, and I came up with a workshop that was held last year back in October. And I'm just going to read this to you just to kind of set this up. But the X-Ray Surveyor is one of the large astrophysical mission concepts which may be studied by NASA in preparation for the 2020 U.S. Decadal Survey. We've talked about these decadal surveys a lot, so you should know what they are by now, but they're a really important thing astronomers do every 10 years to decide what they want to do. And the goal is for the observatory to have excellent, at least Chandra-like, another X-ray observatory, which we'll talk about, angular resolution, while providing a factor of 30 to 100 higher throughput and a significantly larger field of view for sub-arcsecond. And it's going to be it's going to have a suite of science instruments that could include a high energy, high definition X-ray imager, a microcalorimeter, and a whole bunch of other things which we're going to talk about. And with these capabilities, the X-Ray Surveyor will be able to detect and characterize extremely faint objects, as well as study physical processes in a very wide range of astrophysical settings. So, with that, that's all it's going to do now, just those things. So, you know, no pressure or anything. But yeah, that sounds like a really amazing thing that's getting off the ground. So joining me to talk about these things is I'm just going to introduce their names, and then I'm going to have them tell us a little bit about themselves and what they do. So, Alexey, I'll start with you. Dr. Alexey Vikhlinin is from the Harvard Smithsonian Center for Astrophysics. Hi, Alexey, and welcome. Tell us a little about yourself.
Nice to be here.
So tell us a little bit about yourself. All
right. So I'm a physicist by education. I'm an astronomer at Harvard Smithsonian Center for Astrophysics. For research, I do cosmology, study galaxy clusters, distant universe, and I'm a community co-chair for the X-Ray Surveyor study.
Nice. Welcome to our hangout. Thanks for taking time out to join us. Also with me is Dr. Jessica Gaskin. She is at Marshall Space Flight Center in NASA. Hi, Jessica. Welcome.
Thank you. I'm Jessica Gaskin, and I'm the study scientist for the X-Ray Surveyor mission.
Well, so you're a point person up at Marshall, huh? Okay, good. Welcome.
Sure.
Also with me is Dr. Laura Lopez. She's from The Ohio State University. Hi, Laura. Welcome.
Thank you. I'm happy to be here. So I'm Laura. I'm a professor in the astronomy department at Ohio State. I am a member of the science and technology definition team for X-Ray Surveyor. In general, I work on the birth and death of stars and how those events affect the interstellar medium, the surrounding space. And so my expertise is in how stars are born and also how they die in supernova explosions.
Good. And finally, we have Dr. Steve Allen. He's from Stanford University. Welcome, Steve.
Thanks, Tony. Pleasure to be here. So I, like Jessica, am a member of the X-Ray Surveyor study team. I'm a professor at Stanford. I work on galaxies, galaxy clusters, and cosmology. And I guess I've been working in X-ray astronomy for about 20 years now.
Okay, well, great. Welcome to all of you. This is going to be a really exciting one because I do a lot of hangouts. We talk about a lot of things, and we talk about a lot of areas of the spectrum, but the X-rays is the one that I have yet to really delve into a lot, so I'm looking forward to learning a lot about not only this new project, but also what's currently being done. And so with that in mind, Alexey, can you give us just a little bit of a primer on where we stand right now in X-ray astronomy?
So we have X-rays. Let me start with just giving the viewers general idea of what X-rays are looking at in the universe.
Okay, that's better.
To produce X-rays, you need very hot gas somewhere, in your line of sight. That gas needs to be heated to millions of degrees. Okay, and this can happen only in extremely interesting objects or extremely interesting settings in the universe. So whenever we look and we detect X-ray emission from the sky, we know that something really exciting is happening. There could be a black hole, there could be a neutron star, there could be a huge explosion going on, or there could be some of the most massive objects in the universe. So X-ray astronomy started about 50 years ago with some balloon flights. People wanted to look, what's coming from the sky, and they were really had very little clue of what to expect, right? And since then, we've made an enormous progress in sensitivity. In those 50 years, the sensitivity of our X-ray telescopes made the same leap as going from naked eye to the Hubble Space Telescope. Okay. So we now have facilities that can detect extremely faint objects and look very far. Still, the best observatory that we have, Chandra X-ray Observatory, in terms of effective area, it has the same kind of aperture as 15-inch optical telescope. a lot of what our viewers can have in their backyards. You cannot do serious science with a 15-inch optical telescope, but we can do really serious science with Chandra X-Ray Observatory. So what we are up to is we'd like to increase the sensitivity for a future generation observatory by up to a couple of orders of magnitude to give us really powerful tool to look at extremely interesting objects in the universe, to the edge of the universe.
Okay, well, I put up this graphic here that you guys sent me before the Hangout that shows most of the observatories, well, a lot of observatories that we have up in space or have been up in space looking at these various parts of the spectrum. And Alexey, what you were saying about hot gas is kind of illustrated by this a little bit here. We've got everything going down to radio, which is basically down on, those are ground observatories, NRAO and the Atacama large millimeter, submillimeter array. But we also have this from space. We're looking all the way from the microwave, from the Planck instrument. Spitzer does infrared. Hubble does a little bit of infrared and visible and UV. So it's a little bit, it spans a little bit of all of those areas. Followed by the SDO, which is Solar Dynamics Observatory. It's looking at this. And then finally, I want to just go here to Chandra and Fermi. These are the high energy observatories that are up in space. And down below here is a sort of a temperature gradient that you're talking about here. So this is in Kelvin, and we're talking about temperature here as a function of, I guess, wavelength or however you want, X-rays being around 10.
What kind of temperature you need to produce emission at a certain wavelengths to which these observatories are sensitive?
Okay, so in the case of Chandra, for example, it needs very hot gases to be able so on the order of 10 million degrees to be able to get any sort of photons from it. Is that right?
Correct.
Okay,
that's
good.
Exactly correct.
All right, good. So these Jessica, these can really only be done in space, correct? I mean, these are the kinds of observations we need to be out in space for, right?
That's very much true. So our atmosphere is very, very good at blocking X-rays. That's great because it helps keep us alive.
Yeah.
We have done balloon-borne payloads and sounding rocket payloads to observe X-rays. If it's balloon-borne, it must be higher energies. There's soft X-rays and hard X-rays, and that just is basically a measure of the energy of the photons that we're measuring. So you can do some balloon studies, for example, but usually you need to get into space to really make the highly sensitive observations that you need to make.
Okay. So I want to put up this because Alexey sent this out earlier, and I think it's a really good example of what these telescopes do from a general comparison. And so Alexey, I wonder, I'm just going to pull this up, click on me, and if you want to just tell us a little bit about what this animation is showing us here.
So this movie emphasizes the difference between the mirrors we need for X-rays and mirrors we need for optical and infrared wavelengths. So what you've seen in the beginning is called normal incidence mirrors. So you reflect light at approximately 90.
That would be these right here.
That's correct.
Okay.
You cannot reflect X-rays at this type of incidence angles. X-rays will be absorbed in the metal, so you can only reflect X-rays if they bounce off the surface at a very small angle. So we have a different architecture for the mirrors. It's called grazing incidence mirrors. Grazing incidence means that it's much more difficult to build up effective area. So you can imagine that you cover only a small fraction of input aperture, with these mirrors. So you need to have nested shells of mirrors to collect photons, and this also puts a very stringent requirement on the quality of these mirror surfaces. When Chandra mirrors, for example, were built, they were at that time, at least, they were the best mirror surfaces ever produced by humanity, and they are still very, very competitive today. So this just emphasizes, the kind of challenges we're facing in developing X-ray instrumentation.
Okay, so I just want to kind of dig into this a minute because this is a really interesting mirror idea. Here's what everybody's used to seeing. We're used to seeing this. Light waves or light photons come in. They do what they do in every mirror we've ever known. They bounce right back at you, and you see yourself. Or in the case of telescopes, they focus it down to a focal plane. But here, and you can tell the aperture of the mirror is just how big, how wide it is, right? That in Hubble is 4 meters, and you were saying that earlier when you were talking about the Chandra, that it has the effective of, what did you say, 15-inch optical telescope. So here, as I look at this, the aperture of the telescope is what? These little, there's 4 rings it looks like here. This may not be exactly what Chandra has, but there's is that considered the aperture? Because what's bouncing off of it,
Well, so if you look at this mirror face on, and I don't think this movie has
you might
face
look.
on
You might pull up the PowerPoint presentation slide showing that side view.
All right, hang on just a sec. Let me see if I can find it real quick. Go ahead, Alexey.
All right. So when you look at this mirror face on, you will see that only a small fraction of that circle is intercepted by the mirror surface, and the area of that's intercepted by the mirror surface would be considered an input aperture. So effectively, 15-inch, an area that equivalent to 15-inch diameter normal incidence mirror. That would be how much is intercepted by the Chandra mirrors, and they have a diameter of about 2 meters.
Okay. Do I have the right one, Jessica? Is this the one you meant?
It's the last one showing X-rays and X-ray optics.
Okay. All right. Sorry, guys. I'm just. So that would be 2, 3. It's this one. Okay, got it. Here we go, guys. I'm gonna pull this up.
And the idea is, just elaborating on what Alexey was saying, a typical analogy that we use is because X-rays are such high energies, as they have to reflect or bounce off of a very shallow graze angle. And so we take a bullet and have it basically bounce off of a wall. So if you fire a bullet straight at a wall, it either goes through or it stops in the wall, depending on what the wall's made of. But if you take that wall and fire the gun at a very shallow angle, then the bullet will skip off the surface and perhaps go where you would like it to go. So what we do is we have the walls of these optics shaped in a very particular way, so that the X-rays glance off of them, and so they actually are reflected off of the internal surfaces of those optics. But as you get to smaller and smaller angles, so you can focus higher and higher energies, you lose effective area. So you have to build up your effective area by using nested shells, so shells within shells within shells. And that's why you see those rings in that movie of all of the shells together for Chandra. So it's that total effective area that you're really interested in. So let me just to pull up that slide. Is that slide visible to everyone?
Yeah, I should have it up.
Okay.
So if you click on it, you should click on my thumbnail. It should be big for you.
Okay, great. So you can see the picture at the bottom. You have parabolic and hyperbolic surfaces, so that would be one of those full shells that you saw in the movie. And the X-rays from a source would come into your telescope, and if those shells are very precisely shaped, they would be focused onto some type of X-ray detector. So if the surface is very rough, even though you're at a very shallow angle, you could still absorb the X-ray, or it could get scattered off. So the surface also has to be extremely good, so you're not absorbing or scattering the X-rays that you're trying to focus.
Okay, by good you mean with mirrors they're ground to a very fine level of smoothness. Is that what you're talking about? You're talking about the smooth?
Right,
okay.
Smoothness. We have to polish, so we polish them down until they're basically smaller than what the wavelength of an X-ray is. So you're not absorbing the X-rays or scattering them off of those imperfections on the surface, basically, surface roughness. And so it is a very difficult challenge, and as you go to higher and higher energies, you can see why that would become even more difficult.
Well, sure, it's hard enough to reflect these things at all, isn't it? I mean, So the higher the energy, the more it would just want to pass through whatever it's trying to reflect.
And you also go to shallower and shallower angles, which means to build up more area to collect more X-rays, you need more optics. And so it becomes, that's the challenge, is building up enough area to do the science you want to do at the angles that you need to collect the photons that you want to look at.
Okay. And Laura, forget if this is not the right question for you in your expertise, and by all means just say so. But what kinds of material? Well, I just want to make sure that I'm asking the right questions to the right people. And so, what sort of material are the
We only have experts on this science team, you know.
I know, but believe me when I tell you, I've asked questions that, well, this person's better able to answer that than I am. So that's the reason I prefaced it that way. But what kinds of materials are really good at making space telescope mirrors out of?
This is not my expertise, but
I'm happy to answer this question if you would like.
Okay.
I'm looking at the Wikipedia article,
No,
which says that there's an iridium coating.
I just didn't want you to be silent for a really long time, and I wanted to try to get you into it, but I'll come back. Okay. Okay, Jessica. So if you wouldn't mind, could you tell us what sort of materials make for good X-ray mirrors?
So there are two things involved. One of them is what the actual optic is made out of. And you can use nickel, for example, or nickel alloys. In the case of Chandra, it's glass, so a low thermal conductivity type glass. But you always coat it to improve your reflectivity, and so that's where Laura mentioned iridium is one type of coating. You can also use gold. Gold works fine. But you can also do multi-layers and build up layers to give you a different energy response. So there are a lot of things you can do to coat the optics, prepare the optics, improve the surface of the optics, but the underlying material is typically either, you can actually even use silicon, glass, or metal.
Okay, so and the coatings, do they need to be anything special either, or do we coat these materials with anything special?
Yes, they do. So the coatings are things like iridium and gold. So you want a fairly dense, highly reflective coating as well. Okay. So yeah.
All right, so let's move on to the Surveyor then. This is the future in space. We want to talk about the future, although. But before we do that, we should probably talk a little bit about what Chandra's doing. Give us an overview, somebody, of the Chandra's it's one of the great observatories, of which Hubble is that classification, so is Chandra, and it is still up there taking data, correct?
Pretty much so, yeah.
Still up there taking images. Okay, so tell us, Alexey, give us a little background on Chandra. Where is it? Where is it in orbit? And what's it doing?
So it's in a highly elliptical orbit. It takes about 3 days on a 3-day period. So spends most of the time at the apogee for about 2 days and runs long observations of really different kinds of sources. It looks at the solar system sources, so looked at the comets, detected X-rays from the comets. It detected X-rays from some of the most distant quasars in the universe. I actually would like to give Steve and Laura an opportunity to talk about their sites because both of them did really great stuff with Chandra.
All right, go ahead, Steve. Let's get you involved and tell us a little bit about what your work is with Chandra and some of the things that you're using Chandra for, maybe, or in some of the backgrounds that you're interested in.
Okay, yeah, happy to, Tony. As Alexey said, I mean, Chandra can provide absolutely amazing information for so many different targets, but for me, its main uses have been studying galaxies and galaxy clusters, and then using observations of those galaxies and galaxy clusters to probe the large-scale structure of the universe. So getting at things like the nature of dark matter, the nature of dark energy as well. These are things that we can do with statistical studies of large numbers of galaxy clusters and galaxies.
So wait a minute. By looking at galaxy clusters in X-rays, you're able to get a sense of the distribution of dark matter from that?
Yeah, absolutely.
How does dark matter interact? It seems to me that seems counterintuitive. It seems like it wouldn't interact with these high energy.
Yeah, it does seem a little counterintuitive at first, but one of the great things about X-rays is, as we were just discussing earlier, X-rays only shine from objects that are hot. Okay, so a galaxy cluster is actually very massive and very hot, a temperature of about 10 million degrees, and indeed the temperature of the gas gives us a measure of the total mass of the galaxy cluster, all of the normal matter and all of the dark matter combined. So when we look at a galaxy cluster, we can measure its total mass, and with Chandra we can also see all of the normal matter, the gas as well, because it's shining very brightly in X-rays. So we can look at it, measure the amount of dark matter, measure the amount of total matter. It's straight there in front of us.
Okay, and so I'm trying to visualize this. You're looking at galaxy clusters, and just by looking by the fact that it's bright in a certain wavelength in X-rays, you can infer from that its mass, the entire thing.
Yeah, it's its temperature that's critical, Tony. The temperature.
Well, I know, but you get that information by looking at the wavelength of the photons, don't you?
Exactly. Yes, the spectrum of the light.
So that tells you how hot the galaxy cluster is, and from that you get the mass of the entire galaxy cluster, including the dark matter. Is there a way, and I don't know, maybe I'm stretching it here, but is there a way to separate it out, the dark matter from the normal matter, or do you just get a big...
Yeah, there is a way, and it's beautiful, as I said. So the temperature gives you the total mass, and most of the regular matter, the normal stuff, is gas, and that gas is shining in X-rays. So from the brightness of the gas, we can figure out how much gas there is, how much normal matter there is, and then from the temperature, how much dark matter there is. So we can tell how much of both there are.
Okay. So I have here somebody sent me this before the Hangout started. I want to take a look at this observation of the Flame Nebula. Let me get this up here. I believe it's right here. And I just left it on the website because it had this interactive component to it. So here's an observation of star clusters within NGC 2024. And so here, as I mouse over it, you can see that this is the field of view of Chandra. Is that right?
No, that's a composite, I think.
Okay, so here we have X-ray views and then the infrared. But do you see this red in the composite? There's a rectangle.
Oh.
For this. Do you see that?
The box is Chandra's field of view. Yes.
Okay, that's Chandra's field of view. So here's an example of the kind. I mean, this isn't a galaxy cluster. This is a nebula, but we can see in the infrared that it's very bright and that it's you can see all kinds of structure in detail. But in X-rays, you can see these little purple dots. And these are the tiny X-ray sources, well, maybe they're not so tiny, I don't know, within this nebula. Can someone comment on what we're looking at here?
Laura?
So, yeah, sure. So we're seeing the X-ray emission from stars that are in this star cluster, and so normal stars, especially hot stars, can emit X-rays. And Chandra and soon X-Ray Surveyor are able to resolve these stars, and basically, we need good spatial resolution in order to be able to identify that they are individual stars. Otherwise, they'll all be blended together, and so that's why it's important to have a telescope with good spatial resolution. In addition, stars have winds that heat the interstellar gas around them to millions of degree temperatures, and so what you see is some diffuse emission around those stars, and so that is the gas that is getting heated by the winds from the star cluster.
Okay, and so this is another example of the kinds of things that we're able to see using these X-ray telescopes. So I wanted to point that out as well. And let me just stop sharing my screen here for a sec. Okay, so so we're interested in hot gases, things that are hot and highly energetic. And among those, as Steve pointed out, we have galaxy clusters. Another one would be active galactic nuclei, correct? AGNs. Is that another one? And then these supermassive black holes that are believed to be at the centers of most galaxies. And is there any area that Chandra? Well, okay, let me ask it a different way. If we go look towards the future of X-ray astronomy, and we're talking now. We're going to segue into the X-ray Explorer here. What are some of the things that you can't do now that you wish that you're hopeful to be able to do here in the next coming decades? And I guess Jessica, can you give us an idea?
I would say Alexey's probably better suited, or Steve or Laura. More instrumentation.
I'd be happy to take a shot at that one. Okay,
go ahead.
Tony, you just touched in.
And by the way, you don't got to be polite. Just blurt.
It's not a polite crew.
So let me take a shot, because you touched on a few words there that are close to my heart.
Good.
With what we can do with X-Ray Surveyor. So as Alexey and Jessica said earlier, the huge advance is having really amazing mirrors with X-Ray Surveyor that give us maybe 50 or 100 times more collecting area than we had with Chandra, and that really lets us see the high redshift universe in X-rays in a way we would have never have been able to before. So right at the center of things for me are questions like being able to see how supermassive black holes, which you just mentioned, and the galaxies that host those black holes grow and evolve together over time. So in particular with X-Ray Surveyor, what we're going to be able to do is see the very first active galactic nuclei, also called AGN. These are supermassive black holes that are shining very brightly in X-rays as they accrete gas and grow in that way. We'll see those AGN light up at high redshift, and then watch how they change at later times, at lower redshifts, as the galaxies that they're in gradually get pulled by gravity into first galaxy groups and then even larger galaxy clusters that form as time goes on. So at each stage of this evolution, we're expecting new physical processes to kick in. And so if you kind of imagine the movie of what we'll see, at early times we'll just see these point sources, these AGN, incredibly bright sources at a very high redshift. And then as time goes on, we'll start seeing, as well as these point sources, spatially extended diffuse sources, the galaxy groups and the galaxy clusters forming around the AGN. And we'll be able to see the physical interaction between the AGN as they enrich the hot gas in the groups and clusters with metals, as they move the gas around at high speeds, as they make it get hot. And we'll also see in return the physical effects that gas in the groups and clusters has on the AGN and has on the galaxies, because we know there are various processes that come in and which we think really affect how galaxies evolve. So that's huge for me. That'll be really exciting.
Okay. What is the time scale then are we looking at for this project? Now we've mentioned several times on these hangouts and in other venues about this thing called the decadal survey, and I'll just briefly mention it's just sort of decadal means every 10 years. There's a report that comes out where I think where astronomers list their priorities in terms of the science questions they'd like to ask, and among the previous winners were the Hubble Space Telescope, James Webb Space Telescope, and
Spitzer, Chandra.
That's right, Chandra was one. So all of these things come out of a very important report called the Decadal Survey, and they're working on that now and making the case for the X-Ray Surveyor telescope. And so you guys held a workshop, as I said at the top of the hangout. What are your plans? Where are we? Well, tell us a little bit about the survey. What are you guys talking about? Presumably, it's still being designed. You haven't settled on specific designs, I don't think yet. So tell us where we're at with the surveyor. Who should go?
Jessica, do you want to talk about point design, and then we can talk about science?
Thank you. Yes, that sounds great.
Sure. So the teams have recently formed the STDTs, which is the Science and Technology Definition Teams. These teams will define the key science that will be done with X-Ray Surveyor, and from that key science, we will start to design the instrument. So we know that we want a resolution that's no worse than Chandra, for example. So we have some design parameters. We want to have, we know Chandra very well. We know the costing with Chandra. We know everything about Chandra. And so we want to stick with something like that, but with much better optics, improved collecting area, and then also improved detectors. So that's kind of the path. What those actual detectors are going to end up being, and how large an effective area and what energy range we're going to end up looking at, is still to be determined based on the science that the STDT defines as being really crucial and key. So we have a preliminary design that I'm sure if you did a search on Google for X-Ray Surveyor, you would see some presentation come up with a configuration that we've actually done a study on in the past. But this is just a notional configuration that will be updating as we move along. So with that, I'll turn it over to Alexey. Would you like to go into a little bit more on the science that we hope to do after?
So yes, the team is will be working on really sharpening the science case and requirements that we will present to the decadal. But I think it's clear at this point that the main themes will be, this really great leaps in sensitivity and capability, a couple of orders of magnitude in our ability to, to look at faint objects or to run sensitive surveys. And with that kind of improvement, we should be able to reach the very first generations of supermassive black holes shining in the first galaxies. So if you will, James Webb Space Telescope is expected to see the first light shining in the universe, how these first galaxies form. James Webb is not very well suited for detecting supermassive black holes in those faint first objects, but X-Ray Surveyor will be. So X-Ray Surveyor will see the first accretion light in the universe. Accretion is what powers the supermassive black holes. And on the opposite end of sort of scale spectrum, with increased sensitivity, we should be able to get really detailed data on stars in our galaxy, spectra of pre-main sequence stars, young stars, and these dense clusters, how these young stars eject energy and interact with molecular gas that you see in the infrared. So we expect that X-Ray Surveyor science is really compelling, and it really fits together with great facilities that will be coming online in the next decade, both in the space and in the ground. And because of great leaps in sensitivity, X-ray astronomy will be accessible to to a large astronomical community in the ways they've never imagined possible. The kind of data quality that we will be providing will be amazing.
Okay. Well,
so can you?
Oh, go ahead.
I was going to say, can you give us an idea, Alexey, perhaps, or anybody else, what is the leap in terms of, I don't know, energy resolution and maybe even collecting area and so on? So what are you doing above? What do you want to do above Chandra, basically? So if we had to compare this to Chandra.
So with Chandra, this observatory was fit in a normal rocket, but mirrors were old generation mirrors, so they were 4 sets of shells. Each one was 1 inch thick. Okay, so you end up with small collecting area. So the optics that we're developing, we think we will be able to nest 300 shells in approximately the same volume. Okay, so collecting area of the mirrors will be 30 times bigger than Chandra, and we won't lose angular resolution. So angular resolution will remain at Chandra's level, and Chandra is 0.5 arc-second, which is approximately how well you can do from the ground without active optics on an optical telescope. With better detector technologies, in terms of quantum efficiency of detectors, there's another factor of 2 or 3 improvement in sensitivity. Okay, better optical design for the mirror will result in a wider field of view, and we seriously think that we can install a next generation X-ray detector called X-ray microcalorimeter. The first example was just flown on the Japanese mission called Hitomi, which was unfortunately lost. but in the first science observation Hitomi did, it provided incredible wealth of information in terms of spectroscopic observation of a galaxy cluster. Hitomi didn't have a good angular resolution. We hope to combine excellent angular resolution with excellent spectral resolution for X-Ray Surveyor.
I bet that, yeah, I'm glad you brought up Hitomi. I was going to ask you about that. That must have been a pretty sad day, I guess, for X-ray astronomy, wasn't it?
Yes.
Yeah, so for those of you who don't know, it was a Japanese telescope that was launched, space telescope that had launched, and they had lost, it apparently broke up in orbit last month. So it was a pretty sad time for, and as Alexey says, it was designed to have the next generation detector that they want to put on X-Ray Surveyor. So I'm going to ask this to all four of you, but Alexey, as you were talking, it came to my mind. Now, one of the reasons James Webb is an infrared telescope is so that, and you mentioned you're going to be seeing some of the earliest accretion disks in the universe, but one of the reasons that we built James Webb, or James Webb is being built as primarily an infrared telescope, is because those very first stars that you're talking about, the very first light, were actually, at the time they were shining, actually very blue stars and emitted high in the ultraviolet and have redshifted by this time and redshift in the universe into the infrared. So that's where they're the brightest. Don't you suffer from that too? Or do you not? I mean, is it different in X-rays? The early X-rays aren't redshifted any?
It's an advantage for us.
Magic.
Yeah. Okay. It's actually an advantage for us. So the X-rays we see, they don't come from normal stars. The X-rays we want to detect will come from supermassive black holes that sit in the centers of those galaxies. Okay, so the supermassive black hole would have a gas falling in on them and heated to hundreds of millions of degrees, so shining in the X-rays. Now we also can expect that there is a lot of neutral gas in those young galaxies. And neutral gas absorbs X-rays, just in the way our atmosphere absorbs X-rays. Okay. Now, because of the redshift effect, what Chandra sees in the let's say 1 keV band would have to be emitted at 10 keV band if we're talking about redshifts of 10.
Right. Right.
Okay. And 10 keV photons are not strongly absorbed by neutral gas in those first galaxies. So we will avoid the problem of called absorption or blanketing of black holes in the first galaxies by looking at very, very distant objects.
Okay, so even though the very first stars in the universe were themselves very hot, they were nowhere near as hot as the gas that you're observing here.
Correct.
I still don't get it though. They're not redshifted? I mean, it's the neutral gas you're saying that causes it to go down in wavelength? Because I don't.
Neutral gas absorbs 1 keV.
Expanding, right? And so isn't it also causing those photons to go? Well, you're saying go from 10 keV down to 1.
Yeah.
It
so
does happen,
neutral
right?
gas, that does happen. Okay. Neutral gas in the first galaxies absorbs 1 keV photons in those first galaxies. Those 1 keV photons would have been redshifted to 0.1 keV. That's too low for X-Ray Surveyor to see. Okay. X-Ray Surveyor will be detecting photons that have 1 keV energies in our rest frame. Those photons should be emitted at 10 keVs in the distant galaxies.
Okay.
And the 10 keV in that rest frame will not be absorbed.
Okay.
So the expansion is a universal law.
I know that. That's why I'm surprised.
It just shifts and they still remain in the X-ray. That's what Alexey is saying, basically, right?
Okay,
just
good.
in different bands.
Even though they're redshifted, they're not redshifted as much as other photons. Or even they are, but they just stay.
No, they are.
Well, okay. I just want to make sure I'm understanding the.
Put it another way.
That's a great point.
I'm getting a lot of flack from my guests here today, and I don't know what I'm gonna have to do something about that. All right, I know what I'll do. I'm about to set up a quiz show. Here's a quiz show for X-ray astronomy, and I'm going to start with questions from our audience, and the person that answers the most questions wins the game. And let's start with Max, or with that window. MVM Labs LLC is asking, what are the expected false positive contamination that could occur from the X-Ray Surveyor instruments, as, for example, from detector calibration periods? What are the expected false positive contamination that could occur from the X-Ray Surveyor instrument?
Okay, let me give one last bit of trivia before I shut up and.
Oh no, you can answer.
So you might be interested to know that X-ray sky is extremely dark. Okay, so the background that we detect in the Chandra detector is very, very low. We detect in a per resolution element, Chandra detects one background photons every 2 months. Okay, so it's almost impossible to get a false positive. We see 3 photons with Chandra somewhere in the sky, and we know there is a black hole in that direction.
So
Just
you
3
see anything
photons.
bright in X-rays, you're looking at something real.
Yep.
Okay, good.
And we'll often fly calibration sources as well, so our detectors can stay calibrated.
How do you do that? I mean, what do you throw up a what? Well, what's a calibration?
Small radioactive source that that the detectors can see.
Of a known, and it will emit a known amount of X-rays, and you can see if your detectors do these
at a known energy
degrade over time. Do things like the mirrors, the conical shells on Chandra, for example, the reflective surfaces, the detectors, do they degrade over time?
They can become contaminated, or they can also have radiation damage because they are silicon-based detectors. So if you are exposed to high levels of radiation for whatever reason, you can get degradation. But in Chandra, the case of Chandra, you can actually close the door. I guess is it close the door on Chandra as it goes to the radiation belt? Or does someone want to comment on that?
So
anyway,
we move detector out of the focal position. So it's not degraded when we go into radiation belts.
Okay.
So the optics don't focus those particles onto the detectors because it's moved off to the side.
Okay, so that would be the danger from that. It sounds like would be from nearby radiation, then, not necessarily from these distant objects, then.
Right.
Okay, good. Okay, well that's good to know. All right. Well, let me look at Twitter. I saw a couple of things on Twitter. Andrew Planet asked early on. Let me get that question in now. Will the X-ray surveyor be able, and this may be for you, Steve, will the X-ray surveyor be able to see if and when black hole high-energy jets slow down, cool down, coalesce into matter? Will it be able to see those things?
Okay, yeah. So the study of jets is. By the way, could I ask someone to mute?
Yeah, I hear the echo too.
The study of jets is something that the surveyor is going to be absolutely wonderful for. And indeed, Chandra has been absolutely wonderful for this already. One of the things that Chandra revealed to us was in nearby supermassive black holes, how the jets from these black holes, or rather from the regions very close to the black holes, coming out at relativistic speeds, inflate huge cavities, tens of thousands of light years across, near to the central black holes. And yeah, indeed, the material that's coming out from the jets, magnetic fields, very highly charged particles, moving very quickly, they fill these cavities, generating a lot of radio emission that we see with radio telescopes. And indeed, by observing this process, we've been able to do something we couldn't do before. What the X-ray data let us do was measure quite accurately the total power that's coming out in the jets from the regions close to the black holes. And we saw that indeed, most big galaxies at low redshifts, the supermassive black holes do have jets, and those jets really are remarkably powerful. You know, if they were an engine, they would be the greenest engine that you've come across. Incredibly high efficiency at converting matter falling onto the black hole into energy in these jets. So yeah, Surveyor is going to be absolutely wonderful for studying these things.
Wow, that's great. So that's good. Thank you for that great question. So I went through and muted a lot of you. So I think it was Alberto that had the echo in there. So just so you know, George Caldwell is asking: does the fact that X-ray telescopes have to be placed in space place economic limitations on the missions? I mean, I guess most space telescopes have to worry about the cost of going into space, but you sort of have to build that in, right? Right now, as you're deciding on the mission parameters and the budgets, I suppose that's just built into it, correct? Oh, I muted you, Jessica. Sorry. I was trying to figure out where the echo was. There you go.
Okay. That is true. We do have to be in space to do the kind of science we want to do. But I have to say there are a lot of very large ground-based observatories that are also quite expensive. And so as we look across every wavelength and try to reach farther than we've gone before and build larger and larger aperture telescopes, those costs are converging, I guess. I mean, you're talking about the TMT, so the 30-meter telescope, which is not currently being built but being considered, and then
that's not going to be cheap.
It's not going to be cheap. And there's also that very large European telescope. There are lots of ground-based telescopes which are extremely expensive, but they provide a capability that is just pretty phenomenal. And we're mentioning a lot about different wavelengths. And you went to the Chandra page and you showed also different wavelengths and what they show. But that's a really important message, is that without X-rays, you can't get them with the ground-based observatories in combination with other ground-based observatories. You have to have a space-based observatory or you're going to be missing part of the puzzle. So yes, it may be a constraint, but I think it's a constraint for everyone in terms of the future of astronomy.
Exactly. Okay, Laura, did you want to add something?
Oh, yeah, it is true that we need a space-based observatory, so it's worth whatever the cost in order to get this view of the electromagnetic spectrum. I think Alberto wanted to ask a question.
Oh, sorry. I thought
That's
you were
okay.
referring to that question. Go ahead, Alberto.
That's okay. I have a couple of questions, but the other question I had for the surveyor was, so we detect X-ray from supernova remnants, like Flame Nebula, for example. And I know Laura has written papers on this thing. So will surveyor do the same thing that we can do with Chandra nearby, so to speak, at large distances? So can we detect those kind of supernova remnants?
Yeah, so the improvement in sensitivity will allow us to detect, faint sources as well as more distant sources. So we know that right now we know of 300 supernova remnants in the Milky Way, and based on the rates of supernovae that we see in external galaxies, we would expect there to be something like a few thousand, like 3,000 supernova remnants, but we only know of 300, so we're missing 90% of the sources that are likely in our own galaxy. And so I think the improved sensitivity will allow us to detect, the sources that are on the other side of the galaxy that we haven't seen yet. I think also we're missing ones because we have such a limited field of view. With Chandra, we're missing large chunks of the sky where, once we're able to do a larger scale survey, then we'll be able to identify many more new sources.
Cool. Thank you, Laura. Okay, I've got a really good question here on New Star I want to ask. I'm running out of time, so I want to get as many as I can. Is it possible the New Star will contribute to the 3D construction imaging, especially for the black holes research with the X-Ray Surveyor? So New Star, for those of you who don't know, is up right now. It's an X-ray telescope. New Star, will it contribute to the science that's being done with X-Ray Surveyor, especially for black hole research? Anyone?
I can help a little bit and just say that we haven't finalized the energy range yet of X-Ray Surveyor, but in general, New Star goes from 3 to 80 keV, and right now we're mostly focusing on soft X-rays with X-Ray Surveyor, so lower energies than what New Star probes. So I think New Star will have a very important role in observing the hard X-rays that we haven't finalized it yet, but probably we will not cover with X-Ray Surveyor.
Okay, hard and soft X-rays. You're going to have to give us a quick little, what's the difference there?
Yeah, so usually when we talk about soft X-rays, in the case of X-Ray Surveyor, we're focusing on, something like 0.2 to 10 keV, and so usually when people talk about soft X-rays, they're talking about like below 2 keV, for example. And NuSTAR is the first focusing hard X-ray telescope, so it goes from 3 to 80 keV.
Okay, and so I want to get to, okay, again with MVM Labs, you got a lot of good questions, dude. The Wide Field Imaging Spectrometer designed for SmartX, the SmartX concept, I don't know what that is, hopefully you do, has some similarities with the HDXI requirements. Why was no single CMOS development chosen for the X-Ray Surveyor? You guys understand that question? Because I don't. Why no single CMOS development chosen for the X-Ray Surveyor? Does that make sense?
So I'm not sure, but that is one of the instruments that we're considering as a high definition type imager. And we are considering a CMOS sensor for that if that's one of the instruments that we're going to go with. There are several developments for that type of sensor active in the community right now, so we have not made a selection though. So it's kind of in the future. So I'm kind of putting that question off, but it's a good question. But
okay.
Yeah.
Okay.
There's a couple of technical approaches for CMOS detectors, different architectures, and if you take the total of 2 or 3 approaches that being studied, they meet all of the requirements that would be needed for the high definition imager, but these requirements are not met in a single device. That's why we still need a parallel development for the instruments.
All right, thank you. Oh man, they're going to let anybody into this chat window. Somebody named Alberto Conti is asking, Chandra was launched by the shuttle, which is not available anymore. If this new mission is similar to Chandra, do we need to fold it in order to launch it? Good question, Alberto Conti.
We do not.
We do not need to launch it.
Well, as it's for the notional concept that we've developed, it would fit inside of an Atlas V 551 rocket. But since we haven't finalized the configuration, if we go larger than what the notional configuration was, we may need a larger launch vehicle. But since we're not launching for another 10 years or so, maybe more.
But you got to get the decadal survey first, right?
That's right. We don't quite know what launch vehicles will be available, but under the current notional configuration, it would fit inside of without folding, without retracting, it would fit inside of an Atlas V 551.
I was just saying that it's because Northrop Grumman builds foldable things. So.
Okay.
Yes.
Are you working right now, Alberto? Are you?
No, actually, it was a serious question. It was a serious question. Because
if we went to a longer focal
length,
maybe.
There you go. If it goes to a longer focal plane, that's fine. That's the real question. Thank you.
Well, Diane Pasha is asking, we're running out of time, I want to hurry, is asking a really good question. This is with respect to the data that come off of these space telescopes, and in particular Chandra and X-Ray Surveyor. What kind of bandwidths are all these crafts capable of? Is there still bottleneck issues with downloading data off of them? For example, Hubble uses, I think it's TDRS to get the data down. I think New Horizons, is still transmitting data from the flyby from Pluto. So what kind of bandwidths do these things look at, or are they capable of? Anybody know? Download speeds, things?
Give me 1 second. So we would also use TDRS, Deep Space Network type communication, but we're also considering the future of telemetry, which could be in something like LADI, which is like a laser communication system, and that it's one area that's actually making a lot of progress technology-wise. So once again, it's so hard to predict what you're ultimately going to be using, but what our requirement is now, it is met with the current standards, So I can't remember what it is off the top of my head, though.
No, I don't. Yeah,
data rate requirements are not strenuous for X-rays, because instead of sending big images, we send information about individual photons.
Right. I see. So you don't have big square arrays per se.
No. Well, we have square arrays of detectors, but we're finding those photons, individual photons, do onboard processing, and then send down just information about individual photons.
Okay, so the size of the data in X-ray telescopes is usually smaller than, say, Hubble.
Yeah.
Okay.
By a large factor.
Okay, good. So good question. So you don't need as much in that way. So let's see. Sorry, I should have had this queued up. Okay, I'm going to read this one again from MVM Labs again. According to a new study from the North American Nanohertz Observatory for Gravitational Waves, we know about gravitational waves now, has shown that low-frequency gravitational waves could soon be detectable by existing radio telescopes. So that is a comment. So thank you for that. I appreciate it. Please, someone make a large launch vehicle, Andrew Planet is saying. A larger one. Larger than the one than SLS. That's pretty long.
They call SLS. So there you go.
Yeah.
Okay, well, I guess with that is perfect. I got through most of them. And check Twitter just ever so quickly. We got them all. Okay, good. So that's it. All right, we got through it, and we are now out of time. But I want to thank my guests. I really appreciate Dr. Laura Lopez, Dr. Jessica Gaskin, Alexey Vikhlinin, and Steve Allen for taking time out of their day to talk to us about this. I want to thank you all very much. This has been a really great hangout. And you guys going to come back when you guys get into the queue for launch?
Sure.
Because you know what's going to happen. We got to do this X-ray stuff. It's important.
We got to do them all.
Yeah, we got the infrared. We got the infrared covered with JWST, and so yeah, we've got the radio covered with ALMA. So now we need the higher energy. So definitely.
Nice.
By the way, how much longer is Chandra going to be around? Do you guys have I mean, I know there's mission life, there's the mission definition, and then there's what we would like to have. How much longer do you anticipate Chandra being around?
There's an official answer for that, and I believe it's 2030.
Wow, really that long? Wow, that's great.
Possibly.
Good. So then, will there be some overlap, do you think, between Chandra and this telescope? No. Okay. Yeah, they managed to keep Hubble going long enough. They're going to try anyway to overlap.
They're so much more capable than Chandra that, yeah.
But interesting, Chandra's mission was 5 years, right? The base mission, now it's 17.
That's right.
It's been 17 up there.
17 years so far, so it's approaching, boy, it's getting up there like Hubble is. All right. Okay, guys, Harley, Alberto, we got another one under the belt. Harley, do you have some idea what we're doing next time?
Yeah, we may have
We have a choice, don't we?
as we were talking about, we may have a little surprise topic for, I think it's June 17th is the third Friday of June, the third Friday of that month, and there is some surprises out there.
Yeah, so we got one of two. One of them I don't think we can talk about, but the other one when we'll decide, I guess, as time gets close. But we hope you guys will tune back in next month for the next Future in Space Hangout. Also on the first Friday of every month on this channel is the Footsteps to Mars Hangout. So we hope you'll catch those out as well. On behalf of Harley Thronson and Alberto Conti, I want to thank you all very much for watching, and we'll see you next month. And as always, keep looking up.
Thank you.